Okay, so for our second talk, this is about applying equality saturation to electronics design automation. So in electronics design automation, EDA is a very important problem that suffers from phase ordering between different stages of the compilation. So our next speaker, Jingtao, will introduce this work that teaches us how to optimize simultaneously both at high level and low level.
Hello everyone, I'm Jingtao from UC Santa Barbara, and I'm going to talk about my, this is a joint work with Sijie on our improving equality saturation for EDA via semantic e-graphs, and here are my collaborators. So we have two contributions, and we introduced a e-graph variant called semantic e-graphs that capture the semantic equality instead of only the syntactic equalities, and we implement a EDA framework called Nextmap based on the semantic e-graphs that bridge the higher level and lower level abstraction. So more specifically, at hardware EDA compilation flow, it's word level and bit level, and we run more synthesis passes simultaneously than the previous eqsat tool. So first, about our motivation. Hardware synthesis is like the compiler for hardware, and there's long passes, a long pipeline of passes. Like there's an open source tool called Ulysses, has around 50 or more passes for one FPGA backend, and all of them are like manually ordered. So there are two kind of passes we are caring about. One is about optimization, which is backend independent transformation, and we also care about the technology mapping, where we want to lower the netlist into the target primitive. We are targeting the FPGAs, so we care about lookup tables, flip-flops, and DSPs. And the mapping quality influences the quality of results heavily, including the area, delay, and power. And today, actually, the mapping tool is traditional mapping tool is doing syntactic pattern matching. So for the block like DSP, lookup table, and VRAM, they have a hand-coded library of syntactic patterns, and the mapper will pick this pattern. Like only there's an exact syntactic match, we can do a matching here. However, this is problematic, and here is a very common failure pattern. And suppose a previous pass output the expression like 8 multiplies the b plus c. However, the encoded pattern in the DSP library is the sum multiply a. We don't get this DSP mapped, and this will end up in worse performance. So the reason is syntactic matching only matched one form at a time. So this is where the equality saturation comes in. So equality saturation removes the single form limitation. We can maintain all the equivalent expression in the same E-class, and the mapper can match against all equivalent form, extract only once at the end of the flow. However, this is not true between stages, because synthesis pass has a lot of stages, and at each boundary we have to extract one form from the previous stage and hand it off to the next one. For example, we may do the optimization in equal saturation, but hand the result to the separate mapper, and the phase ordering issue returns. So here's an example. Suppose we have, it's the same DSP example. Suppose we have the original e-graph, and we can add a red pro for distributivity, and we're even saturating it more. So the extracted term, we can assume it's a multiply b plus c. It's extracted and marked in green. And the mapper searches for the sum multiply a pattern, so it fails and just use more resource, then we can actually do better, where we can do the mapping inside the e-graph, so we can successfully have the DSP this design mapped in a single DSP. Okay, so our goal is to run more synthesis stages simultaneously in one e-graph, but there are some problems that makes it not that straightforward. So the first thing is there are a large spectrum of previous eqsat work, including like Rover, Seer, eSing, and all this tool is limited into a single stage. They're working for a specific optimization goal and work only at one level, and none have been run on like both optimization and mapping simultaneously, and none have been on both word and bit level. So our take on this is that there are no prior eqsat representations that can really bridge the word and bit level in one egraph. And so the second problem is the direct syntactic word-bit bridge is like will expose the egraph. This is a very classic egraph issue. If we use the Verilog slice and concat by syntax, for example, with a 3-bit signal S, we have like 4 different forms of expressing it in the egraph, and this will give us actually exponential many different forms to be rewrite and discovered. So our fix is to use the underlying semantic equality that the underlying bits of 2-bit vector is equal, means that the 2-bit vectors are equal. And the insight is very straightforward, but we can use such semantic invariant to replace the exponential many syntactic form. So there's another question: how do today's engine maintain this invariant efficiently? Actually, we can do an implementation within the eClass analysis framework. So we can make a relation of has bit for a bit vector to has its concrete bit in a vector. However, it's not efficient. Computing the bits directly is cheap, but maintaining the equality is not. At least we need 2 different direction of propagation of the equality, either a forward direction where we want to propagate the equality from the bits to the bit vector, or we want to do the backward propagation from the bit vector to the bits. And we need to do pairwise comparison between the bit vector or the class analysis facts. So this is our motivation for introducing semantic egraphs. And so there are 3 problems, and we have 3 ideas. In order to deal with the phase ordering issue, we bring the multi-level representation, and in order to deal with the direct syntax bridge explode issue, we introduce the semantic EID, which replaces the opaque EID and reflects the semantic value of the E-class. And in order to maintain the invariant efficiently, we have some operator like semantic constructor and decomposer to make this happen. So let's have a review from the egraph EID. Traditional egraph has the opaque EID, and it's an opaque identifier could be an integer that represents the egraphs, but not carrying its semantic meaning. And we are replacing it with a semantic identifier from a user-defined domain, and it is the E-class semantic value. And there is a concrete value for the successful interpretation case, so we can merge the equal SEID classes. And we also have the fallback case where we return a symbolic SEID, which is equivalent to the opaque EID. So we have the semantics as the first class element in the egraph. And in order to maintain the SEID, we use the egraph X3 operation add, merge, and rebuild, and add some small semantic extension to it. For add, we add a semantic constructor. For S-merge, we add a semantic decomposer, and we all know that AG implementation is lazy, so some union happen at S-merge will be delayed to the rebuild. So we are also doing similar delay for the SEID update, and we will need to propagate them in the rebuild as well. So for insert, this is the standard insert or add, and what we add is we compute the SEID via a semantic constructor. For this case, it's a concat, and if we find a semantic EID that already exists with another E-class, then we find a free equality, or we can just do the merge. So the constructor can establish the equality at insertion, and this equality is not discovered with rewrite rule. And for as merge, what we add is if both SEID we have for 2E class are like composite type, and we can have a semantic decomposer to split the merge into component merge, and this can happen recursively. So basically, we're propagating the equality downwards to its component. And we also have rebuild. So what we are doing in addition is the rebuild process can propagate the SEID in both directions, either upward through the recompute of the semantic constructor and of the affected parents, and also if some merge happens, we may trigger the downward propagation by the decomposer. And it reiterates through a fixed point. So we have some property. The SAG is sound because our equality comes from either the syntactic rewrite rules or from the relation derived by our semantics. So no like fake equality are invented, and we are maintaining the list congruence of these two relations. So it's sound, and also rebuild terminate. And we are back into our Nextmap tool. We have the tool for hardware implemented based on the semantic eGraph, and we are working on a simple domain. So the bit vector SEID is the vector of its underlying wire, and we have some hardware eClass types like the wire vector and register, and we also have cell, which are like primitive operation over these types. We have both bit level and word level logic gates and adder, mux, slice concat on word, and some DSP or technology dependent resource. They will be selected at the extraction. And here is a slice concat round trip example. The goal is to recover the like we originally have a 4-bit wire vector, and we first do the slice and then do the concat, and we are maintaining their SEID in the process. So we can find the concat node has the same SEID as the original wire vector. So there is a automated merge happening here, and without red growth. And here is another example for cross-level synthesis of an adder. So we have a type of bit blasting rule, for example, to a 2-bit adder. We have the word level expression in the eGraph, but we use the rewrite rule to make the bit level like netlist implementation in the eGraph as well. So suppose we have another 3-bit adder, and it's also bit blasted. We can tell that the lower 2-bit of the 3-bit adder are the same as the 2-bit adder output. So the reason this can happen is the word level slice sharing can be propagated from the bit level netlist. So the takeaway is the word level and bit level together in one eGraph can expose us more possible sharing and more optimization opportunities. So here's our workflow. We have the RTL in and have the semantic eGraph do the search and optimization and mapping, and we export everything into IOP constraint and do the extraction and output the map design as a final result. And all our synthesis passes share the same eGraph. We have technology-independent rewrite, including the arithmetic, bit blasting, and some logic, and some retiming. We also have technology mapping rule for based on a user-supplied tech lib, and we have target cells like DSP, DRAM, expressed as rewrite rules. We actually have some recursive pattern for target some repetitive cell structure. And on our extraction, after the saturation, we do some encoding in IOP to extract a type-consistent implementation from our stack. And the general model is there's a binary variable pick one cell from each E-class, and we have the constraint for driver consistency, and we minimize the resource cost. And we have the legal loops checking. So basically register our model in our design. So the feedback loop are expected, and we don't allow the combinational cycle, but that's actually automatically handled. The third point is we have the timing aware constraint encoding by the critical path based on like passed by the eClass and eNode. And the combinational loop will imply the unbounded delay. So because we have constraint on delay, so we will automatically eliminate the combinational cycle issue. And for the complex technology cell, we deal with some non-uniform input-output timing and internal pipeline issue with the split and bind method. And for our evaluation, we have two research questions. The first one is Nextmap's quality, like how is the quality compared to the existing tools? And the second question is, does the running optimization and mapping simultaneously actually helps? So we have two more in paper. And for the first research question, we compare against EOSIS and commercial tool. Compare against EOSIS, we are better on every resources and overall 25 fewer DSP at scale. Compared to commercial, we are competitive and they're sometimes better, but we are overall like at the same scale, and we have some benefits in some designs. So the running time is like overall short, and for largest 400,000 wire size design, we run for 32 minutes, and both time is in ILP. So we are competitive with a commercial tool at scale. And we have an evaluation study for Nextmap against the phase order Nextmap, and we have identical rule, but they are executed in separate phases with like instruction between each, and we can say that Nextmap always ties or beats the phase order Nextmap, and we can sometimes gain very substantial gain from it. So our conclusion is the problem is the prior eqsat tool stopped at one stage, and we propose semantic egraph to get more semantic equality efficiently from the SEID as the first class of encoding of semantics. And we implement the Nextmap tool to bridge the word and bit level, do more synthesis passes at once, and get competitive result to commercial tools. And this enables optimization beyond the reach of vanilla eqsat-for-EDA. And actually, beyond hardware, we believe this should generalize to any domain with like composite type or some structure, semantic value, including string set polynomial. So we can see there could be some potential there for future exploration. Okay, so that's all. Thank you.
Well, let's thank our speaker. We have time for about 2 to 3 questions.
Cool, thanks. I'm Elam from MIT. I'm just curious, just one question about your evaluation. Did you hit the same critical or the same max frequency on everything? And did all of the evaluations take the same like wall clock or cycle count duration? Like, is it doing any like wacky, pipelining or anything that?
I'm not exactly the person doing this evaluation, so I'll suggest you check with Sijie.
Okay, thanks.
I have 2 questions, and the first is basically the same. And USIS is basically not considering the performance. It does not optimizing the find node, something like that. And maybe that's why the evaluation is not reporting the max frequency. And my next question is, the method seems quite general and may be applicable to multiple backends beyond FPGA, right? And but in experience, different backends may have vastly different performance based on, even they are optimized through identical paths. So I'm wondering if there are any subtleties behind this selection of
Okay, thanks for the question. I think for the first one, even though I'm not sure about the detail, I think the framework can support different kind of like we can weight different kind of optimization go together. We can include the fan in, fan out, the power, the area. If you have some estimation over it, we can add it into the IOP like formula. That's doable. And for the second question, yeah, I think it's very exciting that we are actually, we start everything from like working on EDA with equality saturation. So and then we come with a tool and we want to like develop a series over it to like explain what's happening here. Definitely. We can try more other semantic domain that may have different implications there. I think it's generally like very promising, but there are also some issues that different semantic domain may influence the maintenance of the SEID. So we may not lose, we may lose some like good property we can claim here, but it's still like I think it's very exciting to be explored.
Okay, let's thank our speaker again.